Hi there and welcome back to Triplicate, and today a new project, and as you might have guessed, batteries, rechargeable batteries are the focus of this new project. And as you might have noticed, I have quite a few of them. These are only the spares that aren't being used at the minute. And to charge them up, I have a battery charger which I've had for a good number of years now, and it works fine. As you can see, the red means it's charging the batteries up, the green ones are charged, and the red flashing means it doesn't know what to do with them. So it might be absolutely stone flat, it might be fully charged, or it might be a dead battery, which it is in this case because I pulled it out of my box full of dead batteries waiting to go to recycling. And they do fail after a bit, and there's nothing worse than going out with some battery powered piece of equipment and finding it dies in a few minutes because one of the batteries in it is dead. So I built this little gadget, which is a cheap quartz alarm clock off eBay, with a battery socket in the top, and hopefully you can see there are 6 1 ohm resistors in series across here. Now the clock draws no current whatsoever effectively, so this is at 1.2 volts, the nominal voltage of a nickel metal hydride. It's drawing 200 milliamps. So if it's on for 5 hours, then that's 1000 milliamp hours. So we can measure the battery capacity crudely, and it works quite well. The real problem with it is if you leave it going, it will drain the battery absolutely dead flat because it's running into 6 ohms, which doesn't do the battery any good. And I also have a couple of drills, quite old now, but powered by nickel metal hydride battery packs. That one's 18 volt and I think that one's 14.4 volt. They both come with chargers, but they're pretty crude, basically just a resistor in series with the power supply, and you've got no way of telling whether the battery's full or not. They generally say if it's warm it's charged up. So I have been wanting to build myself for quite some time a battery charger stroke discharger that'll measure the capacity, it'll assess whether the battery's still in good condition, and charge it up, discharge it, charge it up, so I know that my batteries are in good shape. Okay, in the rest of this video I'm going to look at the circuit design and go into a bit of MOSFET theory, sort of to back the design up. And some of you might find this a bit dry, and if you do, please feel free to move straight on to the second video where I'll start building and testing the electronics. Okay, so here it is, the proposed circuit of the battery tester charger. Shall we have a look at what's going on here? Firstly, we notice there are 2 power supplies. V supply is 12 volts. Because that's about the maximum an Arduino likes into the power socket, not obviously into the USB socket. But we might want to charge up 18 volt drill batteries. Well, we do. So V charge can be up to 25 volts. At some point I'll come up with a better arrangement for this, but for now that'll do. Right, down here you'll notice a block marked current source. We'll have a look at that in a minute, but all that does, it takes a PWM in from the Arduino and draws a current related to that PWM. and here we have I sense, which is a voltage out that allows us to measure that current, and the current flows between I in and ground. As I say, we'll have a look at that in more detail in a minute. This circuit is capable of charging and discharging batteries using the current source block, and to select which is which, we have a relay driven by a transistor from a port line in the Arduino. So let us consider the situation for charging. Here the battery positive current flow is highlighted red and the battery negative current flow is highlighted blue. So you see the negative end of the battery is simply connected to ground, and the positive end of the battery is simply connected to the current source. So the current source discharges the battery in a controlled, predefined way. Right, when we're charging a battery, if we look again at the red, which is the positive connection to the battery, that goes straight to the V charge supply, and the negative side of the battery goes straight to the current source. So the current source is controlling the rate at which the battery is charging. Okay, so the current source will measure the current we're charging the battery at, but we'll need to know the voltage across the battery as well, and that's what these 282k and 410k resistors do. Now you notice here that this set of resistors is measuring the voltage at V charge into A0 and A1 on the Arduino, the analog inputs, and this set of resistors is measuring the negative side, voltage at the negative side of the battery, into A2 and A3 on the Arduino. And why 2 analog inputs per voltage measurement? Well, when we're discharging a single nickel metal hydride, we'll need to measure down to about a volt. And the Arduino analog to digital converter has 2 references conveniently, one at 1.1 volt and one at 2.5 volts. So say we're measuring 1.1 volt, we're actually measuring a fifth of that, which is 0.2 and a bit volts. So we're measuring, and the voltage reference is at 1.1 volt, so we're actually measuring, our actual value will be a fifth of the maximum, which gives us a decent resolution. On the other hand, when we're measuring 25 volts, which is the maximum we're going to allow V charge to get up to, the topper here, A0 for instance, will be at 5 volts, which is fine, but that is the maximum we can put into the Arduino. The inputs don't like more than 5 volts. However, this one will be half that at 2.5 volts, and given we have a 2.56 voltage reference in the Arduino, yes, we can measure that. So that's why we have that, so we can measure anything from 1 volts to 25 volts with reasonable accuracy. Okay then, shall we have a look at what the current source block's doing? Okay, we're going to develop our current source circuit block using a circuit simulation program, LT-Spice, because it's a lot quicker than building it and finding it doesn't work and having to order some more components and build it again. Now LT-Spice is free, which is a very triplicate friendly price, but it does have some drawbacks. It's a bit eccentric to use, and it never seems to have components that you actually want to use that are readily available. However, we can certainly move forward using it to a point where we're more confident about what we're actually soldering together. Now, this current source block has to operate down to a volt i.e. one nickel metal hydride cell that's almost flat. So I decided to use an N-channel MOSFET to control it, because when they're on, their resistance is very low, i.e. the voltage across them's very low. So I've built a little circuit here with an N-channel MOSFET transistor in, just to get a handle on how they behave. So this voltage here is 10 volts. It just sits at 10 volts. That's a 10 ohm resistor. This is the MOSFET. This resistor here isn't really doing anything because the gate on an FET draws negligible current. Now this voltage source here ramps up between 0 and 10 volts over a second. So shall we run it? Let us look at first the voltage across the gate. Well, let's run it. There we go, and we get a little graph. It needs to know what we want in that graph, so we're going to try that voltage. So that voltage is just, as I say, ramping up from 0 to 10 volts over a second. So let us consider the voltage across the FET. That's the blue tracer, and we can see the voltage across the FET is at 10 volts, so the FET isn't conducting at all till the gate voltage gets to about 3.7 volts, and then it turns on very sharply, and it turns fully on with a very low resistance at 4.24 or thereabouts volts, probably a bit less. So we need to bear this characteristic in mind. We can also, there we go, look at the current through that resistor, which, well, that's the right hand scale, so that current through the resistor, as you'd expect, shoots up to maximum very quickly. Okay, so here it is. Right, V1 is our PWM voltage. Just for simplicity, that volt is actually a steady voltage going between 0 and 5 volts, just derived from the PWM and a resistor and a capacitor, and we know that works, right? So V3 is just the 12 volt supply, and V2 over here is the battery, which is 1.2 volts and 0.05 ohms internal resistance. And here is our FET, and that has between it and ground a 1 ohm resistor, and that is the current measure. We measure the voltage across that and it gives us a measure of the current. We just saw that the MOSFET turns on very sharply, so that resistor also allows us to control the amount of current, because the resistor, the voltage between the gate and the source will always try and be about 4 volts. So as we raise the gate voltage up, the source voltage will also increase, and with it the current through the resistor. We'll see this working in a minute. So R7 and R6 drop the PWM voltage down to about 1/3, because we only want half an amp through half an amp max, and in 1 ohm that's half a volt. So we want to reduce the voltage going in. Again, we'll see this working. And these 3 resistors and the Zener actually bias the gate. This means with V1 at 0, the gate is at a voltage where it's just below turning on. So the transistor will start to turn on when V1 coming in gets to half a volt or something. Oh, we shall see. So, shall we run this? There we go. So let us have a look at our input voltage. There we go. So let's see how this relates to the gate voltage. So that starts at 3.5 and goes up to 4.5. So that looks like what we want. Shall we see how that relates to the current through R1? There we go. So we can see that for the input voltage, it starts to come up when the input voltage gets to about 1.5 volts and reaches nearly 500 milliamps when the voltage gets to 4 volts. So that actually gives us some decent control over the current. Okay, so we have a circuit, we have a large piece of strip board to chop some off, and we have a bunch of components courtesy of Mr. Farnell. So shall we get the soldering iron out and see if we can build something? So now we have a circuit, so if you want to see it getting built and see whether it works, you'll have to wait for the next video. So that's it for this video. If you like the channel, please subscribe. Leave a comment if you've got anything to say, thumbs up maybe. So for now it's goodbye from Triplicate, home of interesting electronics. Goodbye.